Basic electricity and electronics explained. Reactive circuits. Number 7. Parallel resonance. The condition of resonance as described for series circuits can also exist in a parallel combination of inductance and capacitance. For any given values of inductance and capacitance, the frequency at which parallel resonance occurs is identical to the frequency at which series resonance occurs. Resonant frequency, FR, equals 1 over 2 pi square root LC. The properties of a parallel circuit are based on the action that occurs between the parallel inductance and capacitance. Because this circuit has the ability to store electrical energy, it is often referred to as a tank circuit.
Let's see how an ideal tank circuit works. If a voltage is momentarily applied across the circuit, the capacitor is charged to this applied voltage. When the applied voltage is removed, the capacitor discharges through the inductance. The discharge current creates a magnetic field around the coil. When the capacitor has discharged, the magnetic field around the coil collapses. This induces a current in the same direction, clockwise, which charges the capacitor in the opposite direction.
When the magnetic field around the coil has collapsed, the capacitor again discharges, but this time in the opposite direction, counterclockwise. This discharge current causes a magnetic field to once again be built up around the coil. After capacitor C is discharged, the magnetic field collapses and causes capacitor C to be charged in the same direction it was initially charged.
This circulating current would continue indefinitely in an ideal tank circuit, that is, no resistance, producing a series of sine waves. However, since all circuits have some resistance, the circulating current gradually diminishes as the energy dissipates in the resistance in the form of heat. This causes the sine wave current to be damped or gradually diminished in a practical tank circuit.
When an AC voltage is applied to an ideal parallel LC circuit, the currents in the inductive and capacitive branches depend on the applied voltage and the value of reactance in each branch. IL equals EA over XL. IC equals EA over XC. At resonance, XL equals XC, so the two currents are equal. IL equals IC. But the two currents are 180 degrees out of phase. Therefore, the line current, IT, which is their vector sum, equals 0. The only current flowing is the circulating current in the tank circuit. If no line current flows, as far as the voltage source is concerned, the circuit has infinite impedance.
In a practical parallel resonance circuit, which contains some resistance, this theoretical condition does not exist. In a practical resonance circuit, there is minimum line current and maximum impedance. In most cases, the resistance in a parallel LC circuit will exist primarily in the inductive branch. This is due to the resistance of the length of wire in the coils. Therefore, the currents through the reactive branches of a practical circuit will not be equal at resonance and will not cancel out. In addition, the resistance in each branch causes a phase shift, and the two currents are less than 180 degrees out of phase. The determination of the line current IT will involve the resolution of current vectors. The branch currents are added vectorially by components to find the line current. I line equals IL minus IC. The calculation of the line current, the circulating current in the tank, and the circuit impedance can be done much easier by using the Q of the circuit.
You will recall the Q, or quality, of a series resonance circuit is determined by the ratio of the voltage across the inductance or capacitance to the applied voltage. Q equals EL over EA, or Q equals EC over EA. In a parallel resonant circuit, the Q of the circuit is determined by a current ratio. Q is defined as the ratio of the circulating current in the tank to the line current. Q equals I tank over I line. Since the tank current is dependent upon the values of XL and XC, and the line current is limited by the circuit resistance only, then Q is equal to XL over R.
Remember, every series resonance circuit has an acceptable range of frequencies above and below the resonant frequency, called the resonance band or bandpass. At these 2 points, F1 and F2, the circuit was 0.707 of maximum current.
Parallel resonance circuits also have a resonance band, but it is defined as the impedance versus the frequency curve. The band pass consists of all those frequencies between F1 and F2. With maximum impedance at resonance, points F1 and F2 are equal to 0.707 of the maximum impedance. The resistance in a parallel resonance circuit affects the shape of the impedance frequency curve and the width of the band pass. The greater the circuit resistance, the wider the band pass.
If the Q of a circuit is known, then the bandwidth can be calculated. Bandwidth equals resonant frequency, FR, divided by Q. Circuits with a high Q can better discriminate between resonant and non-resonant frequencies than low Q circuits. Once the Q is known, other circuit quantities can easily be determined. For example, I tank equals Q times I line. I line equals the applied voltage, EA, divided by Q XL, or I line equals E over QXC. The impedance of the circuit Z equals Q times XL, or Q times XC.
Let's use this information to solve a circuit problem. In this parallel resonant circuit, the applied voltage is 200 volts at a resonant frequency of 2000 hertz. The inductive reactance, XL, and capacitive reactance, XC, are 800 ohms each. The coil resistance, R, is 50 ohms. Determine the Q of the circuit, the bandwidth, line current, tank current, and the circuit impedance. Calculating for Q. Q equals XL over R. Q equals 800 over 50. Q equals 16. Bandwidth, BW, equals resonant frequency divided by Q. BW equals 2000 over 16. BW equals 125 hertz. Line current equals E applied divided by Q times XL. I line equals 200 over 16 times 800. I line equals 0.0156 amperes, or 15.6 milliamperes. The circulating current in the tank circuit, I tank, equals Q times I line. I tank equals 16 times 0.0156. I tank equals 0.25 amperes, or 250 milliamperes. To determine the impedance of the circuit, Z equals Q times XL. Z equals 16 times 800. Impedance Z equals 12,800 ohms. By first determining the Q of the circuit, the solving for bandwidth, line current, tank current, and circuit impedance was made easy.
Now let's look at some of the applications of parallel tuned circuits. When a parallel tuned circuit is connected in series with a load, It offers maximum impedance to the frequencies within the bandwidth. These frequencies will, therefore, be blocked from the load. The circuit will function as a band reject network.
By connecting the parallel tuned circuit as the load, the output voltage will be maximum within the resonant bandwidth. This circuit now functions as a band-pass network.
Let's compare the properties of a series and parallel resonance circuit. The resonant frequency, FR, is determined in the same way for both circuits. Resonant frequency equals 1 over 2 pi square root LC. At resonance, both reactances are equal. XL equals XC.
The impedance for a series circuit is minimum, Z equals R. But in a parallel circuit, the impedance is maximum, Z equals QXL. The line current in a series circuit is at its maximum, I total, but it is at its minimum in a parallel circuit, I line.
The quality, or Q, of the circuit is determined in the same manner, XL over R. In a series circuit, the Q can be determined by comparing EL to E applied. In a parallel circuit, the currents are compared, I tank over I line. The bandwidth for both circuits are determined by the resonant frequency, FR, divided by the Q of the circuit. This concludes this series on reactive circuits. Be sure to view these films at least once again to thoroughly understand the concepts and techniques involved in reactive circuits. They are fundamental to all advanced work in the electrical and electronic industries.